Welcome. We're recording and mispronouncing. Welcome to Calculus in the PIA. Extreme values of functions, page 191, but this is some stuff I got from another textbook here. Relative extrema then. Extremes are highs and lows, maxes or mins, eh? So function, f of x. Now let's try reading this stuff here, and it's tough to read a math textbook, but you're going to get used to it. It's said to have a local or relative maximum, a local max, at a value c. So c being a constant of 5 or a negative 2 or something. If there exists an open interval containing that number on which the function is defined, and the function all around that value is less than or equal to the value at c. Remember, f of c represents a y value at a particular point. Okay? Now, look at this here. Below here, you got relative maximums at c. Now let's just see how this part of the definition works here. So here, why is this considered a relative maximum? Because the function part, to the left and to the right of it, is either just about or equal to that or lower than that. Does that make sense? From a picture, it makes sense. Okay. Likewise here, it's pretty obvious here, that's the highest point there. That's a local max or relative maximum. We'll use the terms interchangeably, local or relative. Okay. Also, note in figure 1, the derivative at that point c is equal to 0. Okay. We can find maxes or mins by finding where derivatives are equal to 0, but is that always the case? No, you don't have a derivative that equals, you don't have a derivative defined at that point. So often, maxes or mins will happen at spots where the derivative is either equal to 0 or it's undefined, as in this case, okay? Now, that doesn't always guarantee that it's going to be a local max or min. That's where you look for it. Okay, a local minimum, sort of the opposite, should be. It's where the function is greater than the values of that y value at c. Now look here, where the derivative is 0, the function beside it, they're all greater than. So okay, this makes sense, that's a minimum. This is also a minimum, but here's one where your minimum, you couldn't get a derivative equal to 0. It's where the derivative is undefined, because it's a quantity. Okay, so there's relative maxes, relative minimums. So, following that, what about this? The extreme value theorem. If f is a continuous function, so no breaks, on a closed interval, that includes 3 to 7, or something like that, inclusive, a to b, then the function, f of x, has both a maximum and minimum that's global, meaning the highest ever or the lowest ever. That's what we mean by global, or absolute max is another term. Same thing, absolute, okay, and global, same thing. You can use the word global, you can use the word absolute. Maximum, absolute, minimum, okay? Now let's just take a look at the picture. It's usually easier to understand by pictures first to get the concept. Now this is from your textbook. Now, take a look here. On this interval from A to B, just as was defined in here. It's continuous. Yep, there's no breaks. It's continuous. It's defined on the closed interval A to B. Yep, starts at A, ends at B. And it has a global or absolute maximum and a global minimum in the interval. What is the absolute highest value? That's our maximum. This looks like it's the absolute highest value. That's pretty simple, right? This looks like our absolute minimum because it's the lowest y value on the whole set of values. You notice in between, anything else that isn't an absolute max would be called a local max or relative max. Relative minimum right there. You see why? Because there's other things that are lower, but in that neighborhood here, that's the lowest portion, right? Making sense? On a picture, it has to make sense first, and then we'll see from there. So, okay. We understand those terms. Let's try it without some drawing. Okay, first, this here. I want you, first of all, to label. Now, do you notice that I didn't have a closed interval on here? I, on purpose, put on arrows here, meaning this will continue on like this will continue on like that, forever. It continues on up, continues on down. Will you have any absolute maximums? No. Even functions, like if you had an even function like this, there's no absolute minimum, right? There's an absolute maximum right there, right? And then vice versa, if you had the even function, excuse me, if you had the even function like this, opening up, positive a term, positive lead term, you'd have an absolute minimum but no maximum, absolute maximum. You can have relatives but not absolutes. Okay. In this picture here though, I made sure there was neither. It's an odd function. However it's defined. It's just pasted together a few pictures. So let's see here. Function above has relative extrema but no absolute extrema. Notice that all extrema occurs at x values where the derivative is either 0 or undefined. We've mentioned this before. We call these values of x critical numbers. Now, a critical number, as we say here, is found where the derivative is 0 or undefined. Now, just jotting some stuff down here. What would you call this spot around x equals -1 here, the function value? Relative max or min? Max in this neighborhood. Okay, so let's just jot this down. Relative max. And what about the derivative? We're going to call this f prime of x. Would you be able to, would you believe that would be 0 or undefined then? 0. Yeah, it looks like it could be 0. As rough as it was drawn, it looks like a 0. The next spot, where is there an absolute, oh, I shouldn't have put f prime of x, I should put f prime of -1. Okay, where's my next max or min relative? At +1. Yeah. So, a relative min, because here f prime of 1 is, what does it look like? Looks like a 0, tangent line, the derivative. Okay, good. So if you had the function defined, you'd solve for where it equals 0. You'd get those 2 points for sure. Now the way I drew this should be obvious. This is a relative maximum. A rex, no, relative max. Now, by the way, I accept local max, relative max. The word is maximum, though. I won't mark you wrong if you put max or min, but if you have the AP test and you're using the word, write it out in full. I think they probably would just accept max, but I can't guarantee you that, okay? Max or min. Oh, I wrote it disappearing ink, so that's no good. So I'm going to use the word local actually this time. Just it's the same thing. Local max, relative max. Either word works. What do we know about the derivative here? Yeah. F prime minus, or 3, not minus. Undefined. So this is where you look for a value where it just doesn't work. Maybe you'd be dividing by 0 at that point. Maybe it's where there's piecewise function that doesn't line up right to give you the derivative. Now this one here, I wasn't trying to be tricky, it just doesn't match up very well. This is definitely a min here, right? So local min. And it's debatable, but what would you say about the derivative's value at 7? F prime of 7 is which?
0.
Sure, 0. You could see how there's a little bit of a v there, and somebody could argue, actually, I think technically I didn't line them up right, and it would be undefined. But as long as you're aware of those kind of things, it isn't a perfect match, actually. So really undefined, but I could see approximately 0. Okay. Now, without a picture, I'm not even asking for max or min. What are the critical numbers? As soon as you hear critical numbers, what are you looking for? Critical numbers are where the derivative is 0 or undefined. Now, I gave you the derivative. You don't even have to find it. If I gave you f of x, you'd find its derivative and then do this, right? So right now we're just working on given. So the critical numbers, let's find the ones where it's 0 first. Those, okay, what's that?
Do the top and bottom separately, and then
Yeah, exactly. So first, the first part where the function or the derivative gives me 0, as you were saying, the numerator is all we worry about.
yeah, for the zeros, and then if it's undefined, the bottom.
Okay. So set the numerator. So the numerator equals 0. And remember, we already had the derivative done. So x squared minus 4x subtract 5. I think you could solve this. I'll give you guys 30 seconds or so. It's factorable. Bracket, bracket. So, this isn't the finished product, but these are two of them that we're going to look for critical numbers, right? 5 and -1 would give me zeros from the numerator. And this one's easy enough, so you really don't have to do much. Double check. If I plug those in to the bottom, I don't get 0, right? So they're fine. Okay. That way. Now, where it's undefined, critical numbers where the derivative is undefined. Means the denominator equals 0 in this case. So we just said x 1/3. Really, it's that you can't have 0 in the bottom, right? And then we solve that. Well, this one's pretty easy, right? Cube root of 0 is 0, so a critical number, x equals 0, is the other critical number. All three critical numbers then? Numbers are, I guess we could go from smallest, x equals -1, x equals 0, and x equals 5. Okay. I'm writing down x equals 0, even though it's not in the domain of the derivative, because that's a critical number. It probably was in the function. Might have been. We don't see the function, so we're not sure. More about that later, and you can see how that can happen. Okay. Questions for now? Okay. critical numbers aren't bad to find zeros. It's when you start from a function, you do everything at once. So let's just see here. Analytic, non-graphical, like algebraic methods and calculus methods, to find extreme values. Now, there's 4 steps in this, and it's very important, and actually these 4 steps do come up on my tests, regular calculus 30, the AP test, almost always it comes up on these 4 steps, and it comes up in university math 110 tests. I've noticed it on most finals. They have a question like this. They don't give you the 4 steps. You should just know. And we'll learn to know it by just doing it a few times. So finding the absolute extrema of a continuous function on a closed interval, the absolute maximum, the absolute minimum. First thing you do is find critical numbers for the values in between what you're given. Evaluate the function at each critical number. Evaluate the function at the endpoints of the interval. And then the greatest of those steps, 2 and 3, is the absolute maximum, the least, the absolute minimum. Now I want to just see, going back to the picture, if we understand this. And then we'll do this actually here for a particular one. Find the critical numbers of the function on the interval a to b, evaluate the critical numbers and the endpoints. Now, going back to the first page, you know, I had this a to b with no function given, no real numbers given. But what would be the critical numbers here? I'd say this is a critical number, this is a critical number, this is a critical number, because there's where the derivatives either equal 0 or don't exist, right? You see why you'd test those values? Critical numbers are where maxes or mins might occur. So what you do then is, steps 2 and 3 is, evaluate the function at the critical numbers and the endpoints, because the endpoint might be the, in this case it is the smallest value, right? And the endpoint here is not the largest, but could have been. In this case, though, it's one of the critical numbers that gives you that. So that's why steps 2 and 3 test out all the endpoints and the critical numbers, come up with those possible. And then you find out what your least, that's your absolute minimum, what's your greatest, that's your absolute maximum. That's what steps 1, 2, 3, 4 really is all about. It's easy to understand in pictures. It's not too hard to understand. It's just remembering and doing. So find the absolute maximum and minimum values for 3x to the 2/3. But on the interval -1 to 2, inclusive. Wow, eh? Somebody just stepped on a plastic bag. First thing you do is find the critical numbers. So this particular function, is there any possibility, well, let's do the derivative first. We've got to do the derivative. Because you guys probably don't know that one off the top of your head, the picture. So f prime of x. So I'm kind of doing the first step, critical numbers. F prime of x equals, in this case, try it out. Tell me what you get. So 3 times the 2/3 of 2x, I hear. And then subtracting 1? -1 over 3. Okay. Which, to be more useful when we're finding critical numbers, I'd suggest you write it out without negative exponents if you have them. Okay? If you can factor something, also do that because it's easier to identify. So I'm going to put the 2 on the top, the cube root of x on the bottom. You're fine with x to the 1/3 as well, if you understand that to mean cube root. Yeah. You ask yourself, is there any way this function, this derivative, could give me a 0? No way, right? Because it's always 2 on the top. That's a constant. It can be undefined at 0. Question. Cube roots. Can you put negatives in them?
Yeah.
Yes, you can. -8's cube root, for example, is -2 times -2 times, yeah, -2. It works. So cube roots, square roots, you got a problem with domains, right? But cube roots, you don't. So here, just by looking at it, you don't actually necessarily have to set this here. Undefined, when x equals 0. So critical number is x equals 0. Okay. If you had more critical numbers, you'd list them and find them at this point. I do 2 and 3 together. I'd suggest you do the same. 2 ampersand 3. Now, evaluate the critical numbers and the endpoints, right? What do I mean? These steps. That's what I'm talking about with 2 and 3, right? Set it up and organize it with a T-chart. So let's go in order. -1, okay. 0 is my next one, 2. Do it that way. And then the function, not the derivatives values. F of x. Now, sometimes you can just think of these. Sometimes you can't. This is what we're plugging into. Now, maybe I'll just write this beside here so you can sort of think it through. 3 cube root of x squared. This might help you. That's what the 2/3 means. Sometimes that helps you evaluate things easier, right? Okay. So when you put -1 in there, what does it become? 3. Because you go, well, yeah, -1's cube root is -1, but then I square it, +1 times 3. Zeros are easy. 0 times 3 is 0. This one you might have a little challenge with. What would you call that? Well, the cube root of 2 is not a nice number, is it? It's irrational. So we're going to just call it the cube root of 2, but then you square it? It's to the 2/3, or the cube root of 4 is another way of saying it. Either way, nope, that's entirely legal. So 3 times, you could have it as 3 times the cube root of 4, which is the same as you've said, 3 times 4 to the, 2 to the, got the wrong pen there. 2/3, same thing. But how do I know? Basically, I got to know, is it greater or less than this? Because if it's the max, it's definitely not the minimum, right? It's not lower than 0. It's not negative.
Two would be higher, because the cube root of 2 won't be less than 1, and then you square it.
It'll be larger, yeah, than 3, because you're multiplying. What he's saying is, if this was a non-calculator portion of a test, if you have a calculator, go ahead and type it in, you'll get a decimal. But by logic or reasoning here, the cube root of 2 has got to be greater than the cube root of 1, right? This is, I don't know what it is, but it's larger. And then if you square that, it's still larger than 1. So it's going to be 3 times something like 1.1 or higher. It's going to be larger than 3. This will be the middle value kind of thing, right? Now, if you have access, if this is on a calculator portion, you type it in, you get 4.762. I have that typed in. I'll just put that in blue here. But you should be able to decide whether or not you've got that, right? Make a decision. So now we have our absolute maximum, absolute minimum. So the fourth step, now you don't have to label these 1, 2, 3, 4, but I'm just showing you where the rules fall from. Absolute maximum value is 3. Cube root of 4 when, or alternately 2/3 of 2 is fine. And that's when x equals 2. Absolute minimum value is 0. And that occurs when x equals 0. Now you're going to get used to making statements and stuff like this for a lot of these kind of problems. And I'll model them just because they're necessary, okay? So typically, if possible, you state the value and the corresponding x value, right? The actual value of the maximum is the y value, right? And it occurs at. Sometimes you might want to give the ordered pair the point. But if you say occurs at, 0, 0, well, and say that the actual minimum maximum value is. State the value. Do you follow me? The point kind of answers the question, but clearly state what the value is, if possible. Sometimes you're going to be given questions where you can't give it, and you'll say it occurs at the point where x equals 7 or something like that on a different question. Okay. We've got some questions to try, and I'll just stop this here.
Would we not call